Alrighty, welcome back to 105. Thank you for joining me today. Today we are talking about pointer arithmetic, which is one of the unique features of C, which is both simultaneously the best and the absolute worst feature of the language. So let us get into it. So today's lecture will pretty much mostly be about what not to do. So let's encounter our first error. So what we had before is we wrote this function where we finalized it so that we didn't have to specify how many grades we were going to calculate. We had this array length macro to figure out for us. We let C do everything, and it was all well and good. So anyone have any questions about this program that calculated the average for us? It's pretty nice, right? So we can compile it, we can run it, we get an average of 74. So if we take my advice or the advice we usually give you for courses, it's like, hey, if you have some type of functionality you might ever reuse, you should probably move it to a function. So I might be like, oh, okay, well, I'm calculating the sum of all of the grades. Maybe I want to move that to a function. So I might instead define a function, say that, hey, it takes a array of ints called array, and then I will just move this part in. So let's say go here. So I can generalize this a little bit. So let's call the variable, instead of sum, I'll call it accumulator. Whoops. I'll call it accumulator. I'll shorten it to ACC because I'm lazy. And I'll do this, so I'll just return the final value. So now my argument is called grade or array, not grades. I'm trying to generalize it. So I also want to change grades to be array. So if I do that, now I get the array length using my array length macro for this array, sum everything together in the accumulator, return that value. So now, instead of using that sum, I can actually use my function. So instead of doing that, I can do, sum grades divided by grades length, and so I have to re-put this back in. Grades length. All right, so is that okay? I moved it to a function. Everything should be exactly the same. I would just followed my advice. Anyone disagree with me? This is perfectly good code. All right, so first shock of the day. So I compile it. I, of course, ignore all my compiler warnings because I know better than it. And I run this, and my average is now 31. Wow, the average just went down, didn't it? So what happened here? So now we have to relate arrays to pointers, and now we can actually relate them all together. So looks the same, output is wrong. Before it was 78, now it's 31. What happened? So it seems if you can actually argue about this, that we got 31 if we kind of figured out how we arrived at the number 31. If we're put on our detective's hats and we actually figure that out, it appears that we only use the first two elements in the sum. And here we can check the size of the array. So when you're debugging, one perfectly valid way of debugging is to just use printf and print off some different values. So if I here do the size, say I just try and print the size of grades. Oh, whoops. So D, whatever. So anyone remember what the size of this array should be? Called grades. Yeah. 5? not 5, yeah, 20, right? So size is number of bytes, length is number of elements. So in this case, the size is the number of bytes. So ints are 4 bytes, and there are 5 of them, so total is 20. So if I run this, it should say the size is 20. And then what you might think is that, hey, in that sum function, my array is also 20. So if I just move this here and do size of the array, well, when I call it from main, my argument is grades, and then it just gets renamed to array here, otherwise it should be copied. And if I run this now, it says the size is now 8, which doesn't quite make sense. My array is 20, why does it say it's 8 there? So, to explain this, I have to explain to you how C stores arrays in memory. So, how C stores arrays in memory is it picks, like storing variables, picks a random address, we don't need to know how it gets that address, in order to start the array as we used it before to start a variable. So, the rules are the elements of the array have to be beside each other in memory. So, the size of the element depends on its type. So, in this case, I'm assuming all of my elements are of size int, so they all are 4 bytes. So if I have my grades array like before with the values 75, 83, 99, 64, and 72, the array index I use to get them out of the array was 0, 1, 2, 3, and 4. Arrays are 0 indexed in C. If I wanted to break it down further, the address I would actually use is wherever it starts. So the starting byte of element at index 0 is just wherever the array starts in memory, right? So its first byte corresponds to the first byte in memory. The second int is 4 bytes, starts 4 bytes later. So again, these at the bottom are in hex. So it can have other weird digits of base 16. So the address at index 1 would be wherever the array started plus 4. Then another 4 bytes later is the next number, which is 08. And then another 4 bytes later is hex C. So C is just the hex way of saying 12. And then here, the next one, 4 bytes over is 16. And this makes sense since this is a hex number. That means that this is the 16s column, this is the 1s column, and this is the 16s column, so it's 116. So it means 16. So everyone okay-ish with that. We won't have to know, again, you don't really have to know hex or anything like that. It's just to figure out where it is in memory. So C is very efficient. It knows how arrays are in memory. So it just uses the pointer or this A value, the address that starts the array, to keep track of the entire array. It doesn't care how big it is or anything like that. It only cares where it starts in memory. So any questions regarding that? All right, everything's beside each other. So the rules in C is arrays cannot be passed by value. So C does not create a copy of entire array. Remember before when I said everything is copied by value? That is true. Just arrays are copied by value, but not in the way you think. So C does not create a copy of the entire array. C instead copies the address to the start of the array. So if you have a type like this as a function argument, so int array, if you have it as a function argument, it just gets replaced by a pointer to an int, which is the pointer to the start of the array. In a whole bunch of literature, this is referred to as array decay. So this is whenever you see an array, it can always be converted to a pointer just by using the starting address of it. And that is a rule baked into C that applies whether you like it or not. So in this case, when I did size of array in my function and got 8, it's because that array was actually a pointer in that function. And all of our computers are 64-bit machines, which if we know how many bytes are in a, or how many bits are in a byte, so 8 bits to 1 byte. And if we have 64 bits, that means we have 8 bytes. So on any of our machines, pointers are just going to take up 8 bytes of memory. So just remember also any type that ends with a star is an address or a pointer. So just assume it's 8 bytes. You don't really have to commit that to memory or anything. It will only serve to figure out why we got size of 8 there. So we got size of 8 there because, well, our pointer or our addresses need 8 bytes. So the nice thing about knowing A and just knowing the starting address of the array is we compute the address of any element. So again, assuming I have my array of int where it's 5 integers all in a row and it starts at address A, well, given that starting address A and which is the starting address of an array and an index I can actually compute what the address of the element should be, right? So the address of this element should just be A plus I, like the index. This is also a reason why we use 0 indexes to make everything kind of line up nicely here. So it's just generalizing it, A plus I times the size of int. So in this case, the size of int was 4. So the address for the first one is A plus 1, then A plus 4, then A plus 8, then A plus 12, then A plus 16, right? So the nice thing about C is, well, we didn't actually have to do that size of int and multiply it and do all that stuff before. We didn't have to do that ourselves. C automatically uses that size of on the type pointed for when computing that address using pointer arithmetic. So it turns out I can write something like A plus 1. So if I write A plus 1, this uses that index and it will compute that address above. So if I take the address A and add 1 to it, I get this as my resulting address. So it will take the size of the type pointed to into consideration and not just give me, you know, the value literally A plus 1. Everyone okay with that? Ish, kind of a little bit confusing. Getting into memory, getting us prepared for doing 241 and doing hardware. That's why we're doing C. So, just to be clear, you can only perform addition and subtraction with pointers, so this is why we call it pointer arithmetic. It's a bit special. It does that size of and everything based off the type. So if I have a pointer to an int and I call it A, well, if I do A plus I, that pointer arithmetic is going to result in the address. Usually we don't really care about the address, but just to differentiate between the two, it will result in the address A plus I times the size of int, which in this case would be 4. If instead I did double, if I had a variable called b that was a pointer to a double, and I did b plus I, that means I result in the address b, which is the starting address, plus I times 8 because a double is 8 bytes. Then if I have this really confusing one, which is char star star, so it's a pointer to a character, well, if I do C plus I, the type that I'm pointing to is a char star, so which is still a pointer or an address, so the size of that will be 8. So it will result in the address C plus I times 8 because it's holding a bunch of addresses. And if I do pointer arithmetic by dereferencing C, so remember dereferencing C means essentially I just get rid of a single star in its type. So if I dereference C, the resulting type is a char star, so it's a pointer to a character. So if I take a pointer to a character and add I to it, well, it will take the size of whatever it's pointing to. In this case, char is always 1 byte. So it will result in the address, whatever the address, the dereferenced address of C is, plus I times, in this case, 1, because size of a char is 1. So questions about that might be slightly confusing. Again, we don't test you on like what the addresses is on stuff. Just good to know when things get really weird, which they kind of already did. All right, so C guarantees the order of elements in memory. So this is a term that you'll enjoy saying as people that program. We say that array elements are contiguous, which means they're just all together in memory. They're all in a row. So that's just a fancy word, just means all stuffed together. That means there's no wasted space between them. So it uses addresses A plus, 0, so the starting address, all the way up to enough memory to hold 5 ints in this case, so 20 bytes. So the hex 14 is just the same as going all the way to byte 20. And like in math, if I have the square brackets, that's inclusive. If I have the rounded brackets, that means exclusive. So it won't use offset 20. It means the last byte it's going to use is like all the way up to 0, all the way up to 19, right? Exactly like our array indexing. So in other words, we're using the addresses, if I don't want to write it in hex, A plus 0, A plus 1, all the way up to A plus 19, which is 20 bytes, which holds all of my 5 integers. Everyone still with me? Okay, so using pointer arithmetic, I can actually access any individual element I want. So assume I have my in array called grades like before. These are all their addresses. These are all their indices and then their values. So if I didn't want to write square brackets or anything, I could use pointer arithmetic if I want to. So grades plus 1, that's pointer arithmetic. So grades is the pointer to the start of an array. Plus 1, that's pointer arithmetic. So it will point to the element at index 1. So this would be the second element, 83. So if I dereference that pointer, so if I dereference, A plus 4, then I get access to that actual value, 83. So turns out that the syntax to access an array element is just for your convenience. You can write one or the other, they mean the same thing. So before we wrote grades and then square brackets index, turns out it's just a shorthand. What it really does is save you from writing dereferencing yourself, because what it really does is take that and transform it into pointer arithmetic, where it does grades plus index and then dereference it. But these two things are exactly the same. They will do exactly the same thing, but you should always prefer the array syntax. In this course, if you actually do pointer arithmetic, you have screwed up royally and should not be doing that. So you might be doing pointer arithmetic for like 241 or something like that. You should not be doing that in that course. The only time you should be doing pointer arithmetic is when you're accessing elements of an array, in which case you should use the square brackets and save yourself the headache. Whew, all right, so that was a lot of talk just to explain what these square brackets do, but now you know what they do and you can promptly forget it. So, size of an array, the rules for that is the size of an array is only valid in the same scope you declared it in. So, in this case, otherwise there's going to be pointer decay because, well, if I use a function, I could call it from a whole bunch of different functions. I'm not guaranteed my array will always be the same size, so it doesn't make sense for that sum function to know that the array size is 20, because it might not be 20 the next time someone else uses that function. So there's always going to be pointer decay in when we have a parameter. So it just becomes a pointer. So in order to successfully write my sum function that uses the array, I have to add another argument that tells me, hey, what is the array length in this case, because I can't figure it out because this thing will just get decayed to a pointer. So going back to this, if I was to fix this program, I can't just try and figure out the array length from within here, because, well, this thing is actually a pointer. So I have to do something like this, where I just add another argument called array length, then just delete it from here. Otherwise, it is the same. And when I use the function, now I have to pass two values. So I have to pass the address to the start of the array, which is just grades, so that will be decayed to a pointer, and then the array length, which in this case I can just pass grades length because, well, I can use this array length macro on grades because it is declared in the same function here. It's declared in main, so using it is perfectly fine there. It doesn't become a pointer there unless I try and use it in a different function or anything like that. So if I go ahead, whoops, and do that now I see that, hey, I successfully moved sum to a function. Now it's giving me the right answer again, and I can rejoice and hopefully not hit the microphone again. So questions about that? So this is going to be useful for lab 5 when it comes out because you'll be using arrays. If you decide to make your own function and then just use an array, you're going to get all sorts of problems. So you're going to have to pass the array length there. Some people don't use C because, like Java will kind of bake in the length to an array slightly differently. C is meant to be super simple, so it just becomes a pointer, and C hopes you just use it correctly. All right, so this is another fun one. So these are more details that are not needed for this course, and the rules may vary depending on CPUs and operating systems. But this will help us figure out things that will go wrong. So addresses for variables and functions. So variables in your functions, if you talk to programmers with more experience, they'll call them local variables. You can call them local variables now. Sound really smart. They start at a randomly picked address, and by default, they start at this randomly picked address SP. It's short for stack pointer. You will know what a stack pointer is again once you get into more details on how computer works. But a stack is basically, if you go to the cafeteria and there's a stack of plates and you put one down and you take a plate from the stack, you'll always get the plate on the top, and if you put them down, well, the first one you put down is the last one you're going to take out because it's now on the bottom. Stacks kind of behave exactly the same way for that for storing variables. So variables will be put also in order at lower addresses from the initial stack pointer. Sometimes there'll be space between the variables, sometimes not, again, depending on your computer. So you should not actually do pointer arithmetic. So let's take this program as a little example, knowing what we know about memory now. So here I declare a local variable if I want to be smart, or just a variable in main called x and initialize it equal to 1. So again, I write main in a green line, and above it is all of the values, all of the variables in memory. So after this line, I have the variable x in memory. Its value is 1, and its address, I'll just pick a random address where the stack pointer started at and gives me an address. So it might get an address back like something like 1FFC. Again, this is in hex. I just made up an address. So the rules are, well, if I declare y, initialize it by 2, well, there's now 4 bytes that store the value 2. I can refer to it in my code through y, and it would be at the next lower 4 bytes. So it might be at the address FF or 1FF8. So these are 4 bytes away from each other. Again, depending on your machine, it might be a bit further away, but this is what it looks like on my machine. So if I do Z, same idea, it gets the value 3. It might be stored at address 1FFF4. Then, if I declare a variable called P, it's a pointer to an int. So it takes 8 bytes, right? And it is an address, and the value of that address, well, it's pointing to Z. So in this case, P would be storing, at this 8 bytes here, it would be storing an address. We now know, in this specific example, the address it would store, if it's pointing to Z, is 1FF4. And it would have to store it. It needs 8 bytes to store that. It might be stored at 1FE8, something like that. But we can just draw out our pointer like before. So it's pointing to Z. So now, if I did P plus 2, anyone want to tell me what the resulting address of P plus 2 is? Yeah. 1,6? F16. So it should be pointing to some value that's on there. So P, the address stored at P is 1FF4 plus 2. Or what is it pointing to at the end of this? So pointer arithmetic, right? So, whoops. So P is a pointer to an int, right? So it's an address. If I do plus 2, that's pointer arithmetic. So the address that it results in, again, we don't really have to know this, but the address it results in, well, it depends on what P is pointing to. So it's pointing to an int, so it will move forward 2 integers, right? Which is 8 bytes. So in other words, it's initially pointing to this. If I do pointer arithmetic, it will jump forward 2 integers. Turns out X and Y are also an integer, so that would essentially just jump, and then point to this, right? So it would be pointing to X now. P plus 2 would result in this address. And then if I dereference it, I can access this value in memory. So if I change it to 4, what am I changing? X's value of 4. So now if I print off X, the value of X, Y, and Z, well, now we get a nasty surprise. So if I run this now, I get that nasty surprise of, hey, I changed X, right? So I changed X through doing pointer arithmetic by accident. So if I just normally look at this code to argue about it, if I didn't have this stupid pointer arithmetic here, like if I didn't have these 2 lines here, and I gave this to you, you would just say it prints x1, y2, z3, right? But now, through magic, which isn't magic, it's just dumb pointer arithmetic, I can actually change X through doing some fun pointer arithmetic and knowing how things are laid out in memory. So if I did, here's a quiz. If I did P plus 1, what does that change? Y, right? Again, don't really have to notice this. We will not ask you about this on exams, but it is good to explain how your code has screwed up. So yeah, in this case, now that changes Y. And C doesn't really care. It doesn't have to be invalid, or it doesn't have to be valid. I could do something like -1, right? Well, actually, in fact, this again is just short form for the just using the square brackets. So when I had it at, I don't know, 2 before, well, this is exactly the same thing, right? These 2 lines mean the same thing, so I could instead just do P square brackets 2, and that will also, whoops, compile, run it, that will also change X, because they both mean the same thing. So that's why C doesn't care about what number you use here, because it's just going to do pointer arithmetic on whatever number you give it. It doesn't care what it relates to. It will just blindly do the math. So if I put -1 here, that's just the same as just going backwards a number, which I'm also allowed to do. All right, fun questions about that. We have learned pointer arithmetic, which will be a nightmare for debugging. All right, so the data structure that stores your values of variables is called a stack. Notice in all those examples with memory and functions, how I always write them is I'm adding variables to the top, and removing variables from the top whenever I call different functions, or whenever I need to get rid of something, or if we introduce a new scope or something like that. So like I said, the real life analogy of that as an idea is like that spring-loaded stack of plates. The last plate in is the first plate out. And that's the same way variables work in memory. So they get thrown out of memory in that order as well. When you get into algorithms course and data structure, you'll give a name to this. It'll be last in, first out, or LIFO. Again, don't worry about me. I'm just talking to myself. So you don't have to know these rules, and in that example, you may notice there was an unused addresses between Z and P. Again, don't worry about it. That's just magic I had to do to make it work for my computer. Might not work for your computer. That's why debugging is fun. So, question might be, well, why don't I just use pointers instead for functions? So, if there's array decay anyways, if there's array decay anyways, why don't I just do, instead of just array, using an array, which I don't know the size, why don't I just do this? So, turns out you can absolutely do that. That will compile, no problem. That's what's happening anyways. So nothing happens. C is under the hood. Since we're using this to access our array, it's doing pointer arithmetic anyways. Yeah. What is an array again? Array decay is just like whenever I use the array in a, like pass it as an argument to a function, it gets converted to a pointer as just pointing to the start of the array. So whenever you have array decay, it just means I'm just converting an array to a pointer. So yeah, in this case, when I use it as a function argument, so here I'm trying to pass an array. So here grades is actually an array, but when I pass it to a function, I can't pass arrays by value. So it can only pass it by pointer, like copy the value of the pointer. So this is why we call it array decay. This grades array gets decayed to a pointer when we call this function. So this array just becomes a pointer. So if it's a pointer anyways, instead of writing what I had before, like the square brackets here, I could instead just write that, hey, it's a pointer anyways, whatever, just use it as that, and that is perfectly valid. So if I do that and run it, nothing changes. My example still works. It's doing pointer arithmetic anyways. It doesn't really care. So the answer is you should actually prefer in this example to do the first one and not the second one. And it's kind of a matter of style and convention because they mean the same thing to the compiler, but you as a human reading it might get some more information. So if I see int array and then it's with this square brackets, I know it's a pointer, but I know it's a pointer to multiple values. I don't really care if they're contiguous or not. They'll be contiguous. But what I really care is that it's a pointer to multiple values, and I can use it like the array square brackets on it to get multiple values. While if I just give it a pointer to an int, usually that means you're just pointing to a single value. So in this case, conveys some meaning to a human. Multiple values versus single value. So again, your compiler will freely just let you use pointers everywhere. But if you want to have a hope of reading your code again or understanding it at a glance, I highly suggest you use this as your rules to follow. So also beware. Before I said you should, declare all your variables on separate lines, it's because the variable declarations are very strange with pointers. So if I make the following declaration, int star x comma y, the rule of C is that it does not carry that star across commas. So the type of, in this case, x is a pointer to an int, and the type of y is just an int. They do not both have the same type. They are different. So this will especially trip you up if you have not written C in a while and you come back to it and you have to try and remember this rule. It is a fairly horrible rule to remember. So instead of remembering that rule, just declare each variable on its own line with its own semicolon. Do not get into the habit of just doing commas to shorten things. So again, like I said, I'm telling you a lot of rules. Most of the rules I'm telling you is so that you can forget them and follow my one rule. So my one rule here is to always declare one variable at a time, and then you don't have to worry about remembering this. Or you can worry about remembering this and not listen to me, and then you know what actually happens. All right, so another thing, if you can't set a pointer immediately, usually like with variables, we want to initialize it to like something safe. So if you don't know the value of an int, then you should declare it as like int x equals 0. It's like a safe initial value rather than getting some random value, because if we don't initialize it, it's an undefined value or essentially a random value. So in this course, likely you shouldn't set pointers to an initial value, like you should just set them as something you get back from the ampersand sign. But if you don't know the variable or the value of the pointer, you should declare it as equal null. So null is a special pointer that just says, I don't know. Like it's just a safe initial default value that I haven't set it to anything, but it's a known set value. So it's just a special value called null in all caps. And the reason we do that is because dereferencing things like null always generates an error, which is actually easier to debug. So it's a special address. Actually, it's address 0, so you can actually just do equals 0 if you really want. But it's guaranteed to always be invalid. So if I take my code here, so here I set it int star p, so variable called p. It's a pointer to an integer. I set it to null. And then I try and dereference p, so I try and get the value that it's pointing to, and then assign that to the value 1. So if I try and run this program, I'll get another fun error where it says terminated by signal segs address boundary error or seg fault. So this is going to be one of the most fun errors you have when dealing with pointers. So it basically means I tried to dereference an address that isn't valid, which crashing is actually better than like what we did before when we just like randomly changed values and it just kind of happened to work. Crashing is actually a better option than just changing something randomly and just seeing what happens, and maybe some variable you don't want changes. So this will actually save you, and this is called a segmentation fault. You'll get very used to that term as you're using pointers. And it just immediately crashes your program and stops. And if you want to debug it, I might have a lecture where I go over different tools once we get into more pointers, but one tool is called Valgrind. So what this tool does is tell you information about why your program crashed if you have messed up your pointers. So to use it, I type the name Valgrind, then space, and then just running my program as normal. So if I do that, I see it dumps a whole bunch of information, but the information I care about is you scroll up and you find the error. So here, it tells you the error maybe in not the most nice way as a beginner program, but it says invalid write of size 4, which what this is actually doing to our computer is trying to change 4 bytes of memory because it's pointing to an integer. And it's trying to write to it, so it's trying to change that value or assign to it. Write means the same thing. So this is saying I'm not allowed to do this assignment, and it shows us the memory address that we're executing. Again, useless information we don't need to know, but we crashed when we were executing main. In this case, we can see we crashed on line 6. So this gives us some information that, hey, we crashed on line 6, so we have screwed something up. And it also says address 0, which is null that we tried to dereference, is not stacked. So it's not allocated on our stack, or it's not a real address that's valid. We don't know what this means, we don't know what this means. So it's basically saying that memory address is not valid is what it's trying to say. Because if I just got rid of it, right, and I didn't have that, if I didn't have that right, then no problems are going to happen with my program. It's just not really going to do anything. Nothing's going to crash. It's going to be all fine. So that's a tool to use. It will help you debug things. If you see that seg fault thing, use Valgrind as like one of your first things to do. So yeah, segmentation faults are a good thing. Believe it or not, easier to debug because you know how far your program gets. It's much harder to debug if just some random value changes, where sometimes your program works, sometimes it doesn't. And that Valgrind tool, again, you're not required to use it. Maybe I'll show more examples in a bit, but you just use that Valgrind executable and it will tell you why and what line it failed at. All right, another fun thing you might do that this example, sometimes my third years forget this example too. So another rule is local variables only exist when the function runs. So if I have this weird program where I have main, oops. So let's just say I have this program, I have main where I declare a variable called p that's a pointer to an int, and I call foo. So here I'm going to get a value back from this function. It has no arguments, and it's going to give me a copy back of whatever this value is. So in this function, I declare an int x, initialize it to 1, and then return a pointer to x. So if I see what happens in memory to my program, well, before I call the function, main will create a variable called p, set aside 8 bytes for that pointer. Its value is I don't know yet because I need to do the function call. So I'd be calling foo. I don't copy any of its arguments. It has no arguments. It's void. So it would declare a variable called x, and its initial value is 1. Right? So everyone okay with that? So when I do %x, that will give me the address of this 1, right? But if I do that and I return from it, I will return a pointer to whatever that x was pointing, or wherever it was pointing to. But whenever foo returns, that x variable, because it's within foo, doesn't exist anymore. So foo's gone, x is gone. So it's just pointing at the ghost of x, essentially. Everyone okay with that? So at this point, if you run through your program and your pointer points at something you don't know what it is called undefined behavior, and your computer may do anything it wants to. So one option it has is, well, let's run it. So I have this program. Oops. All right. So I have this program. I can do weird things to it if you want. But if I compile and run this program, my compiler is trying to tell me something. It says address of stacked memory associated with the local variable x returned. So it's saying local variables don't exist when the function returns. So that's what it's trying to tell me with that message. It's trying to tell me I'm doing a bad thing, but of course I can ignore it and just run my program. So if I run my program, in this case, it's 1. So it gives me back whatever that value of x is. Right? So if x was 42, and here I'm depending on that, I get back 42. Seems to work. Seems to be consistent, but again, it's technically undefined behavior, and I can show you something weird that happens with it. So right now, it's printing 42, right? If I just, if I just add another line, if I just add another line, it shouldn't change anything. It should still print 42, right? Again, this is why programming is fun. So that is what it means by undefined behavior. So if you're pointing at some invalid memory, sometimes it might work, which is why it's hard to debug, but sometimes it might not, and bad things will happen, and sometimes they'll just creep in with something that seems totally unrelated, like just printing LOL there, and it just completely bricks it. So questions about that? Yeah?
Yeah, I wonder
So the address of x is returned, right? So let's say it gets back address like 1000 is where it lives. So we would get back the value 1000 as the address, but that address doesn't actually store x anymore because after the function's done, x doesn't exist. So it's pointing at that same address, but since that function is done, it's not guaranteed that it'll be x now. So it'll be just some random location, and the computer will reuse it. Yeah. Sorry? Yeah, so x exists while the function runs. So like when I went through it, before we return, x exists. Yeah, only in foo. So x exists only in foo. When foo's done, x is done. All right, must be another class or something. So I'll just show another example or flash another example and you can get to it. So if you want, you can return pointers that are still valid. So in this case, if I try and return the maximum value pointed to by something, I can do that because if I run through this really quickly, the addresses I use in here point to x and y, which exists in main, which are still valid when this function called maxPointer is done. Again, I can leave you with this to ask questions about on Discord and things like that. But when we do this, we'll copy an address. It will be pointing to either x or y, and it will be valid. I can use it. Nothing bad will happen. So just as a summary, be very careful with pointers. Use them only when necessary. Usually only when a function needs to like return multiple values where it just dereference it and writes to it, like scanf or things like that. You should try and write functions that only need to return one value, then you don't have to deal with pointers. And remember, variables only exist in memory at runtime while that function is running. So with that, remember, I'm pulling for you. We're all in this.